The last major type of conic that we're going to discuss is the hyperbola. Remember, we recognize conics by some key algebraic points. Ellipses, if you remember, had an x squared plus a y squared term. Parabolas, which we dealt with previously, either had just an x squared or just a y squared. Algebraically, we want to look for an x squared and a y squared with a hyperbola, but one of them is going to be negative. Geometrically, hyperbolas and ellipses have some similarities. Remember, in an ellipse, the constant came from the sum of d1 and d2, where that d1 and d2 were defined as the distances from any point on the ellipse to the foci. So if we add the distance between one foci and a point and another foci and a point, that's always going to be the same amount. It's a little bit different in ellipses, but in ellipses, the constant is that d1 minus d2. Minus here is a constant. And notice we take the absolute value. Now, this comes important in terms of calculating our A values. If you remember with ellipses, that D1 plus D2 was a constant. So if we look specifically at one of the vertices, and we call this D1, and the distance to the other vertice D2, notice that that D1 plus D2 is going to equal 2A, because A is the distance from the center to a vertex. Well, notice with the hyperbola, if we come down here and look at the value from one of the vertices, if I take this vertex here and I subtract D1 and this distance D2, all that leaves is 2A. So in this case, D1 minus D2 is that 2A value. So the distance from the center of the hyperbola to the vertex is A, and the distance from the center of the hyperbola to one of the foci is C. Just like with ellipses, we have both horizontal hyperbolas, which is what you're seeing here, and vertical hyperbolas, and the equations mimic those of the ellipse. For a horizontal hyperbola, you're going to have x minus h squared over a squared. Again, that a being the distance from the center of the hyperbola to the vertex, minus y minus k squared over b squared equals to 1. Remember that center is going to be hk. For a vertical hyperbola, we switch the order. We're going to have y minus k squared over a squared minus x minus h squared over b squared equals 1. So if the x term is negative, it's going to be a vertical hyperbola. And again, the center here is still going to be hk. An important thing to note here, you calculate your c value, the distance to the foci. C squared is equal to a squared plus b squared, which is a little different from the ellipse. While the standard form does help us find the center and also the foci of the hyperbola, it doesn't give us much information about how flat or how steep the hyperbola is on either end. We're going to see the sides of the hyperbola. Again, the general shape of a hyperbola is it looks like two parabolas back to back. But that general shape is that they are going to approach these two oblique or slant asymptotes that we talked about previously. The equations for those asymptotes can be determined from the equation of the hyperbola itself. If you have a horizontal hyperbola, and I'm going to go back up to our equations here and add these in, the asymptotes for a horizontal hyperbola can be found by y minus k is equal to b over a times x minus h, and then the negative of that as well, negative b over a times x minus h. So notice they're the same line, they're just going to cross each other with opposite slopes. Likewise, for the vertical hyperbola, those asymptotes can be found with y minus k equals a over b instead of b over a times x minus h, and y minus k equals negative a over b times x minus h. And note that these lines or these asymptotes merely create a rectangle. That rectangle, then, we can use the diagonals for. Those are the asymptotes to get a picture of what the hyperbola is going to look like. So for these horizontal hyperbolas, notice that rectangle will have a length of 2a and a height of 2b. And the diagonals create those asymptotes with the equations that we just discussed, and likewise with the vertical hyperbola.